my students, Le Chatelier's principle can just be a bit tricky to really feel confident with. So what I would like to do is to go through some of the questions that we can expect to come our way. Le Chatelier's principle, when a system at equilibrium, and we will just be in honors chemistry dealing with physical equilibrium, meaning we have a substance that is existing in two phases, and so we have one phase change and another phase change, and there's been a balance of the rates. So our go-to has been water in equilibrium in its liquid state to its vapor state. Okay, so when a system at equilibrium is subjected to a stress, and we went over what the stresses could be in the previous video, a change in the amount of reactant, meaning adding or taking away, or a change in the amount of product, adding or taking away. A change in the temperature, so we have a vessel that is containing this system, has some liquid, has some vapor that's, reached its balance. We could change pressure, and usually we're changing pressure by changing volume, so these go hand in hand. So if we exert a stress on a system, how will this system behave to relieve the stress? Okay, that is Le Chatelier's principle. So I found that this kind of fill in the blank that I think might be a decent way to begin our approach. So in simpler terms, Le Chatelier's principle, if anything is added to a system at equilibria, and so we're not going to have Le Chatelier's principle unless we're dealing with equilibrium. The system will try to consume whatever was added. So if anything is added, it's going to try to react it away. If anything is removed, the system will try to replace whatever was removed. So the reaction is favored away from what is added and toward what is removed. So that kind of wording may have just helped you just get a deeper understanding or have one of those eureka moments. So let's apply what this is saying. Okay, so in the following reaction, will the concentration of the water vapor, so that's what I'm being asked to focus on, water in the vapor state. Okay, so will I be increasing or decreasing this when the following stresses are applied? So I know if I shift right, then I'm increasing the concentration of my product. So if I shift right, that means the product concentration is increasing. This is a kind of shorthand way that I can talk about the concentration, the amount. How much vapor do I have in the given amount of space? So those little brackets say all of that. How much vapor, so how many molecules, how many moles do I have per the volume? All right. In other words, how will the system respond to the following stresses? Okay. Well, what if we add water vapor? Well, if we add, it's going to shift away from what is adding. So we are going to be shifting to the left. So if we shift left, then we know we're decreasing the amount of water vapor. If we shift left, the amount of water vapor decreases. Okay, what if we increase pressure? Well, remember, pressure only stresses out gas. Well, where do we have gas? On the product side. So what will the reaction do? This is what's stressed, so we need to decrease it. We're going to shift left, decrease water in the vapor state. Well, what if we remove some of this? Whatever we removed, we're going to shift to replenish. And so we'd be increasing the amount of water vapor. So this will be a shift to the right. Well, what if we increase temperature? Okay. What side needs heat to happen? From liquid to gas. That's our endothermic direction. So if we're increasing temperature, we are giving more heat. That is going to encourage the endothermic direction. We could also look at it like we're adding reactant. And if we add, we're going to shift to remove some of that. So we're going to increase the amount of vapor. But if we also just think about, we're increasing the temperature of our vessel, we're going to give more energy to the liquid to, of course, vaporize more. So that will be a shift to the right as well. So I hope with these examples, then we're getting more comfortable with this. So here's dry ice, solid carbon dioxide subliming. In what direction, left or right, would the equilibrium shift with the following changes? What if we add solid? Okay, well remember, if we add something, now AP students, we're going to revisit this whenever we study equilibrium, but honor students, if we add, it's going to shift to remove it. So this would shift to the right. If I increase volume, okay, that is only going to impact gaseous side. So if I increase volume, then it's as if we're removing gas. It's going to expand. And so the balance will be out of whack because it will seem like we don't have enough gas. So it's going to shift right to make more. If we add heat, well, which is the direction that needs heat? It's the reactant side. So if I add heat, it's like I'm adding reactant or I'm just encouraging that endothermic direction. It's going to go right as well. What if I cool? Well, then it's like I'm removing reactant or I'm encouraging the exothermic. So it's going to go left. What if I increase pressure? Okay, that's going to stress this side. The gas is going to be colliding and then depositing so much more. So it's going to shift left. It's going to appear if we decrease or if we increase pressure, the only way we could have done that is by changing our volume. So it's going to seem like, oh my gosh, we have so much more vapor for the moment. So we could look at it as if that is implied to be an increase in the amount of product. And so it's going to shift left. And then what if I would remove reactant? It's going to replenish to, or move to replenish it. So that would be a shift left also. It's just a coincidence that all these are right and all these are left. I could have, of course, gone from side to side. Why don't we, if you want to pause, give, go ahead and predict, and I'll give us the answers. Solid to liquid, that of course heat needs to be absorbed in the forward direction, and so we could write heat as a reactant. So if we increase temperature, it is going to go to the right. If the system is cooled, it's going to go to the left. If we increase pressure, we don't have a gas here, so no change or no shift. Okay, what about here? If you want to pause, I'm sorry. If you want to pause, and then I'll go through the answers that we should get. All I want us to do is predict the direction of shift. So how will the reaction respond? Is it going to go left or right or no change? Okay, catalyst. A catalyst just speeds up the reaction. It just makes it go faster. So if you're already at equilibrium, it's going to do a whole lot of nothing. So no change. That's kind of, an aside topic. But hopefully, because the vaporization would require the heat, so if we're increasing temperature, we're going to shift right. If we are removing heat, we're going to shift left because it's endothermic, so exothermic in that direction. If I add product, it's going to shift to take that away, left. If I add reactant, it's going to shift right to replenish that. And then if I decrease pressure, that's just going to stress out the product side, so I'm going to shift, pressure if I decrease. It's going to seem, because it's going to expand, like I don't have enough gas, so I'll shift right to replenish it. So give the problems beneath this a try. Once you wrestle with it, try a couple examples, you'll have it. Just really apply the understanding of chemistry that you have accrued. I know you'll do great.